It's a very interesting time in wireless communication because in some ways the technology has evolved to the point where we're close to the Shannon limit in some aspects of wireless communication. So we have tremendous technology around MIMO. We've gotten very, very sophisticated modulation and coding techniques. We're very good at utilizing all of the degrees of freedom that the wireless channel provides us to support multiple users at different data rates depending on their requirements. So some aspects of the wireless technology is very sophisticated. I think one of the areas that's very exciting, and we're doing some work on this in my lab, is how to utilize machine learning, which is a big overhyped research area, but how to utilize machine learning in the design of communication systems. The way they come together in my mind is that machine learning is really good at learning something that's unknown based on a lot of training. So what's unknown in a wireless technology setting? Well, often the channel is unknown. Sometimes you don't even have models for the channel, like in the case of millimeter wave technology. So one of the things that we're looking at is how would you do signal detection or signal demodulation when you don't know the channel? Or maybe you don't necessarily know the waveform because it may be coming from many different devices. You could potentially use machine learning for authentication. So you say, okay, each device has its own unique signature. How do you figure out which device is sending the data to you? But I see kind of machine learning as applied to communications as a very ripe area for new research that can hopefully provide us with breakthroughs in these new technologies that we need to develop. A small group in my lab that's working on molecular communication. So basically, it's still wireless, except the channel is not an electromagnetic channel. It's liquid, and basically the idea is that we're sending data encoded in molecules or chemicals. So for example, one of the demonstrations we did in my lab is we used binary modulation where an acid was a 1 and a base was a 0. And so you have a detector at the other end which is detecting whether you sent an acid or a base. And so it's a very rudimentary form of communication. We got a whopping 5 bits per second out of it, but it allows us to communicate in environments where electromagnetic waves don't propagate well. And so for example, inside the body, you may not be able to build a good radio that can operate. It may not be small enough. It may cause damage to the surrounding organs by sending electromagnetic radiation. So with, the body consists of chemicals, so using chemical communication in the body might be the right way to communicate. And you might think, well, 5 bits per second isn't very fast, but if all you're doing is turning on and off, biomedical devices or monitoring some kind of concentration of medicine or sensing some type of cancer, then perhaps that's all the data rate that you need. And it's something, even in your stereo of the old days, you would have an equalizer that you would use to adjust, to remove the distortion of that intersymbol interference. And equalizers were used up through second generation cellular systems. But then, as the data rates got really fast, you needed a very, very complex equalizer, and it just became too complex to use equalization as a technique to mitigate the intersymbol interference. So in third generation cellular systems, we moved to spread spectrum, and in fourth generation systems, we moved to OFDM. So those are other ways to compensate for the ISI. So we moved away from equalization. Now, with this molecular communication, it's actually coming back, that we need an equalizer because the data rates are low, and there isn't, it's not a very high complex equalizer. So that's the right way to deal with the intersymbol interference. Equalization is also coming back, for example, in some of the new modulation techniques that are being proposed for 5G cellular for very high speed, so high speed trains. I have a book on wireless communication, and there's a chapter on equalization that I was going to take out because I thought it's not relevant anymore. Nobody's using it in current systems. that was, 5 years ago, and now here we are 5 years later where these technologies are coming back for other kinds of systems. And that's why I think it's interesting when you think about 5G to not just focus on what's happening in cellular, but what's happening in the whole wireless ecosystem. Many of these new applications require very low data rates, and therefore the technologies we've developed in both Wi-Fi and cellular to get up to gigabit per second may not be relevant. Another technology that I think is going to become very important in this next wave of wireless is very energy efficient radios. So if you've got a sensor that's, say, embedded in a wall or in your tennis shoe, you don't want to recharge every day. These are going to be running off batteries. Sometimes you can't recharge the battery at all if it's in the infrastructure. So energy harvesting systems where we collect energy from the environment to power these radios. So we need to go back to some of the older technologies or create some new ideas around designing a radio specifically for energy efficiency rather than high data rates. I think about Back to the Future in the sense that older technologies that we've used in the past and kind of fell by the wayside because they weren't the appropriate technologies for where applications and services were going. Some of those older technologies are actually very interesting and maybe the best things to use. What I often tell my students is, when you're thinking about these new systems, don't go read all the papers that have been written. Just try to look at a clean slate and say, okay, if I were going to design a system from scratch and I didn't know anything about how today's systems are designed, what might be the appropriate way to design things? So part of that is just being creative and thinking outside the box with new ideas. And then part of it is this back to the future notion of going back to systems that were built 20, 30 years ago, which had different requirements than today, but similar requirements to what some of the new applications coming down the road have. And that's the best way to kind of think broadly about how we can design systems for this very massive, heterogeneous set of applications that people will be using wireless for.